Regarding the technical principles behind generative large language models, like GPT, a common explanation is that they generate text by predicting the next word with the highest probability. This effect is somewhat similar to the autocomplete feature in search engines. Whenever we type a new character or word, the input box starts predicting the following text, with higher probability suggestions ranked at the top. But how exactly does the model determine the probability of each word appearing? This video will reveal the principles behind ChatGPT for you. In our previous video introducing large language models, we mentioned that when discussing their technical principles, we have to talk about the transformer architecture. Since the 2017 paper Attention is All You Need introduced the transformer, it has virtually dominated the field of large models for text. Models like OpenAI's GPT, Xinhua's GLM, and Baidu's Ernie all have the transformer at their core. In the Attention is All You Need paper, it looks like this, a bit complex at first glance. But don't worry, it can be seen as consisting of two core parts, the encoder and the decoder. Suppose we want this transformer to perform an English to French translation task. We feed an English sentence into the encoder, and the decoder returns the corresponding French sentence. What happens during this process? Let's first look at the encoder part. The input text is first tokenized, meaning it is split into individual tokens. A token can be understood as a basic unit of text. Depending on the tokenization method, short words might each be one token, while long words might be split into multiple tokens. Then, each token is represented by an integer number, called a token ID. This is because computers cannot store text internally. Any character must ultimately be represented by numbers. With the input text represented numerically, it is then passed to the embedding layer. The role of the embedding layer is to represent each token as a vector. A vector can be simply thought of as a series of numbers. To fit it into the visual here, the vector length is simplified to 3. But in reality, vector length can be very long. A question arises. We already represented each token with a single integer earlier, so why now represent each token with a series of numbers? One reason is that a series of numbers can convey more meaning than a single number, containing more grammatical, semantic, and other information. It is like the words man and woman. They both describe humans, but their genders are completely opposite. If represented by only one number, should the difference between these numbers be large or small? But with multiple numbers, we can represent more dimensions. For example, the first number could represent the degree of being female, the second the degree of being older, and the third the degree of higher social class. So, the vectors from the embedding layer aren't arbitrary. They contain grammatical and semantic relationships between words. The embedding vectors of similar words are closer in vector space, while unrelated words are farther apart. This helps the model use mathematics to calculate distances in vector space and capture similarities between different words in terms of semantics, grammar, etc. Moreover, the difference between man and king and the difference between woman and queen can be seen as similar, which can also be represented in multidimensional vector space. Therefore, word vectors can not only help the model understand the meaning of words, but also capture complex relationships between them. For intuitive visualization here, we use a three-dimensional vector space, simplifying the vector length to 3. In the paper proposing the transformer, the vector length was 512, and in GPT-3, it is 12,288. So you can imagine how much information can be contained. After obtaining word vectors through the encoder's embedding layer, the next step is to add positional encoding to the vectors. In the previous video, we mentioned that a key mechanism of the transformer is positional encoding. If you missed the last section, no problem. Positional encoding involves adding a vector representing each word's position in the text to the word vector from the previous step, then passing the result to the encoder. The significance of this is that the model can understand both the meaning of each word and capture its position in the sentence, thereby grasping the sequential relationships between different words. Next, we come to the core part, the encoder. Its main task is to transform the input into a more abstract representation. This representation is also a vector, a series of numbers that retains both the lexical information and sequential relationships of the input text, while also capturing key grammatical and semantic features. The core mechanism for capturing key features is the encoder's self-attention mechanism. When processing each word, the model not only focuses on the word itself and its nearby words, but also pays attention to all other words in the input sequence. As the Transformer paper's title says, attention is all you need. The self-attention mechanism determines attention weights by calculating the relevance between each pair of words. If two words are more strongly related, the attention weight between them will be higher. For example, in this case, grammatically, it could refer to animal or street. The self-attention mechanism discovers a stronger association between it and animal, so it assigns a higher weight to animal. Due to the self-attention mechanism's comprehensive focus on context, the resulting output representation not only contains information about the word itself, but also incorporates relevant information from the context. Context is crucial in language and can reveal different meanings of the same word. So, in the encoder's output, the vectors representing each word are adjusted based on contextual information. The same word can have different abstract representations, depending on the context. The self-attention mechanism involves many computational steps. This video is mainly a simple introduction. More details can be found in the original paper. Moreover, the transformer actually uses multi-head self-attention, meaning the encoder doesn't have just one self-attention module, but multiple. Each head has its own attention weights, focusing on different features or aspects of the text, for example. Some might focus on verbs, others on modifiers, some on sentiment, others on named entities, etc. And they can perform parallel computation, meaning their progress doesn't interfere with each other. The weights for each self-attention head are learned and adjusted by the model during prior training from vast amounts of text. Following the multi-head self-attention, there is also a feed-forward neural network that further processes the output of the self-attention module, enhancing the model's expressive power. There isn't just one encoder in the transformer, multiple are stacked together. Each encoder has the same internal structure but does not share weights. This allows the model to understand the data more deeply and handle more complex textual content. After looking at the encoder, let's move to the decoder. It is key to how large language models generate words one by one. Through the previous encoder, we have an abstract representation of each token in the input sequence, which can be passed to the decoder. The decoder also first receives a special value indicating the beginning of the output sequence. The reason is that the decoder uses both the abstract representation of the input sequence from the encoder and the previously generated text as input to maintain coherence and contextual relevance in the output. In this initial round, there isn't any generated text yet, so the special start token is used as input first. The specific generation process still involves multiple steps. First, similar to the encoder, the text goes through the embedding layer and positional encoding we already know about, then is fed into a multi-head self-attention layer. But it is slightly different from the self-attention layer in the encoder. When the encoder processes each word, it can attend to all other words in the input sequence. However, in the decoder, self-attention only focuses on the current word and the words before it. Words after it are masked and not attended to. This ensures that when the decoder generates text, it follows the correct temporal order. It cannot peek at future words. When predicting the next word, it only uses preceding words as context. This type of multi-head self-attention is called masked multi-head self-attention. Masked multi-head self-attention operates on the already generated output sequence. After that, the decoder has another multi-head attention layer. This is where the abstract representation of the input sequence, output by the encoder, comes into play. The attention here captures the correspondence between the encoder's output and the output about to be generated by the decoder, thereby integrating information from the original input sequence into the generation process of the output sequence. The feed-forward neural network in the decoder functions similarly to the one in the encoder, enhancing the model's expressive power through additional computation. And like the encoder, the decoder also consists of multiple stacked layers. This can improve the model's performance and help handle complex input-output relationships. The final stage of the decoder includes a linear layer and a softmax layer. Together, their role is to transform the decoder's output representation into a probability distribution over the vocabulary. This probability distribution over the vocabulary represents the likelihood of the next generated token, with some tokens having higher probabilities than others. In most cases, the model selects the token with the highest probability as the next output. Now we know that the decoder essentially guesses the next most likely output. As for whether the output aligns with objective facts, the model has no way of knowing. That is why we often see the model confidently stating falsehoods, a phenomenon also known as hallucination. The entire decoder process repeats many times, with new tokens continuously generated until a special token indicating the end of the output sequence is produced. Then we have the complete output sequence from the decoder. Congratulations! The above describes the original transformer from attention is all you need. The encoder is used to understand and represent the input sequence, and the decoder is used to generate the output sequence. In practice, based on the original architecture, several variants have emerged, mainly falling into three categories: encoder-only decoder, only and encoder-decoder. Encoder-only models, also called auto-encoding models, retain only the encoder from the original architecture. BERT is an example of such a model. These models are suitable for language understanding tasks, such as masked language modeling, guessing masked words in text, sentiment analysis determining if text sentiment is positive or negative, etc. Decoder-only models, also called autoregressive models, retain only the decoder from the original architecture. The GPT series are examples of such models. These models excel at text generation by predicting the next word, as we've seen with ChatGPT. Encoder-decoder models, also called sequence-to-sequence models, retain both the encoder and decoder from the original architecture. Models like T5 and BART are examples. These models are suitable for tasks that transform one sequence into another, such as translation, etceterization, etc. After this video, your understanding of the technology behind large language models should surpass that of more than 99% of people. If you are curious about how to actually build a ChatGPT, see you in the next video.